chapter 16, section 8, we'll look at Stokes' theorem. So this is actually pretty similar to what we just did in the previous section. So it says, use Stokes' theorem to evaluate the double integral across S of the curl of f dot ds. Well, what this is saying is we can do the curl of f dotted with ds can be shortcutted by the following. So we're going to have, I want to make sure I use, there's various forms we can use, and I want to make sure I use the right one. So for problem 1, the easiest thing to do is to use the integral of f, plugging in a parametric equation r, or vector r, with respect to t, dotted with r prime of t dt. So that's actually going to be the simplest way to solve 1. And there's various ways we're going to change these curl double integrals. But for this one, that's how we're going to do it. So we get z in this one is equal to, well, first let's write f. F of x, y, z is equal to x squared, z squared. Let me write this in compact form. And y squared, z squared for the y component, and then x, y, z for the z component. Then it says z is equal to x squared plus y squared. So we've seen that plenty of times. Inside the cylinder, x squared plus y squared equals 16. Oriented upward. So again, we're going to have to worry about orientation to make these double integrals positive or negative depending. Okay, so for this one, we're going to have the r vector with respect to t is just going to be, from this we can see r squared is 4, so therefore r is, r squared is 16, therefore r is 4. And so we're going to write r of t as r cosine t, and so r is 4. So this is r cosine t, and then y would be r sine t, but r is 4. Now z is the one that gets messy. Maybe not though. So if z is x squared plus y squared, and x squared plus y squared is 16, then z has to equal 16. So z is 16. Then we find r prime of t. Well, that's pretty simple. This is minus 4 sine t, positive 4 cosine t, and 0. Then we just need, and this is the hard part, the function replaced with r of t. Well, the function is x squared z squared. So that's going to be x squared, which is 4 cosine t, is now going to be 16 cosine squared t, times z squared, but z is 16, so it's times 16 squared. The second component is y squared z squared. Well, y is 4 sine t, so square that, and you'll get 16 sine squared t times z squared, which is 16 squared. And then the third component is x times y times z, which is going to be 4 times 4, 16 cosine t sine t times z, which is another 16. Okay, that's f of r of t. Now the formula says to dot that with the derivative equation. So we're going to have 16 times 16 squared. What does that turn out to be? It's like, oh boy, 4,096, is that right? Yeah, 4,096. And then we're going to, or maybe that's after I multiplied. No, it's not. So we're going to take that times this one. We're going to take this one times this one, and we're going to take this third one times this third one and add them all together. Now luckily the third one is times 0, so that's going to completely go away. So the dot product between those two terms and the vectors go away because it's a dot product, it's going to be, oh boy, might not have enough room here, negative 16,000, this is 4,096 times another 4, 16,384, and we're going to get cosine squared t times sine t, and we're going to get plus 16,384 times sine squared t cosine t, and plus 0, and we're taking all of that as an integral with respect to t. And you can factor out a actually you can't factor anything out other than the 16,000 and a common sine t, it looks like, sine t cos t to both terms. So you have to do those integrals. I'm not going to go through the whole thing, I'm just going to show us part of it. 16,384, you should get 1/3 cosine cubed t plus 1/3 sine cubed t from 0 to 2 pi, and that whole thing turns out to be 0. So we do all that work and we find out that the curl of the vector field dotted with the differential line segment is just going to be 0 for this case due to symmetry. Okay, so that's problem 1. Okay, in problem 2, we are going to solve this. So we're going to have the vector field f xyz is equal to x plus y squared, y plus z squared, and z plus x squared. And we have to find the curl of f. Well, the curl of f is equal to the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z of these three terms. So x plus y squared, y plus z squared, and z plus x squared. And this is a cross product. So this is really I, j, k above these three columns. So this is going to equal to, cover up the first column, partial y with respect to z plus x squared is 0, minus partial with respect to z of y plus z squared is 2z. That's in the I, minus, cover up the middle column, partial x with respect to z plus x squared is 2x, minus partial z with respect to x plus y squared is 0 in the j, plus, cover up the third column, partial x with respect to y plus z squared is 0, minus partial y with respect to x plus 2y with y squared is 2y in the k. So this curl is minus 2z, minus 2x, and minus 2y, and that's going to be P, Q, and R. Okay, so we're going to use this formula, double integral of d of minus P dg dx, you've seen this one before, minus Q dg dy plus R dA. We know P, Q, and R. We just need to find dg dx and dg dy. So in this problem, we're told that we need an equation for z. So we're not giving an equation for z. We're giving C is a triangle with vertices 5, 0, these 3 points. So basically we have a picture in 3 dimensions here where we're going to 5, 5, and 5. And basically we get this triangle. Okay, well from that triangle we can get the plane x plus y plus z should equal 5. So x plus y plus z should equal 5 from that plane that's created from those 3 points. Therefore z, which should be g, which is a function of x and y, is just 5 minus x minus y. And we can also see that x should be bound by 0 to 5, and just like a similar problem, in 2 dimensions when z is 0, y is governed by 0 and this line right here in the xy plane, which is described by 5 minus x. Okay, so we're going to get the double integral of, so this will become 0 to 5, 0 to 5 minus x of negative p, which would be negative 2z, excuse me, times dg dx. dg dx is just minus 1. Then this is going to be minus q, which is negative 2x, times dg dy, which is also negative 1. And then it's plus r, and r is negative 2y. And we're doing dy dx. And what we're going to have is, this is equal to, boy, a lot of negatives here, triple negative, write this. This is going to be minus 2z, another triple negative, minus 2x, and then it's minus 2y, dy dx. But we know x plus y plus z equals 5. So we can factor out a minus 2, and this whole thing would just be in a different order, x plus y plus z. But that whole thing is just 5. So we factor out 5 times 2 would be negative 10. And there's nothing left in the integral except for dy dx. So this is going to give us minus 10 times the integral 0 to 5 of just 5 minus x dx. And if you take that integral, it should be easy enough for you. You're going to get negative 10, 25 minus 25 halves, which is minus 125 when you do that arithmetic out. Okay, so that's problem 2. Problem 3 is very similar, and I'm probably not going to keep showing you all the steps after we do a few more, maybe after this one. So we have f of xy, we have a field xyz, and it's equal to xy, 4z, and 6y. And the first thing we're going to find is the curl of f, which is the cross product, write this one a little cleaner this time, of partial with respect to x, partial with respect to y, partial with respect to z of these 3 terms, xy, 4z, and 6y. So we've got a cross product here of partial derivatives. So cover up the I column, we get partial with respect to y of 6y would be 6 minus partial with respect to z of 4z, which is 4, the I direction, minus, cover up the middle column, partial with respect to x of 6y is 0, minus partial with respect to z of xy is 0, in the j direction, plus, cover up the third column, partial x of 4z is 0, partial y of xy would be x in the k direction. So this curl is 2, 0, and negative x. Is that right? Yes, that's correct. Okay, and that's P, Q, and R. So we're going to use the same equation as the last one. Negative P dg dx, negative Q dg dy, plus R dA. So we just need dg dx and dg dy, and we can do this one. So dg, let's see, what would be z? X plus z equals 10, and x squared plus y squared equal 36. So we're going to get z is the equation 10 minus x. Z is g of xy, which is 10 minus x when I rearrange this equation here. And so we're going to get dg dx equals minus 1 and dg dy equals 0, which means that whole middle term in my equation is going to go away. So I don't need to write it. So we're going to have the double integral of minus p, which is minus 2, times dg dx, which is minus 1. Middle term goes away, plus r, which is minus x, and this is dA. And so we're going to get, the second we see a cylinder, we should think polar coordinates. So we're going to have r squared equals 36, which means r is 6. So we're going to change this to 0 to 2 pi, and 0 to, let's see, this would go to 6 of, this is positive 2 minus x, but x is really r cosine theta, times r dr d theta, to put it into polar coordinates. Okay, let me make sure I didn't make any mistakes. 2 minus r, yep, that looks right. And so these should be easy enough to do. You can't split these up necessarily, so you would have to do 0 to 2 pi, 0 to 6 of, distribute this r, 2r minus r squared cosine theta, dr d theta. And what you should get out of that is, yeah, let me not show you the steps, and this should be a pretty simple double integral for you to handle. You should get the result 72 pi. So that would be problem 3. Okay, for problem 4, we have Stokes' theorem again. We've got F is x squared y, comma 1/3 x cubed, and xy. And this is probably where I won't show the curl anymore. So you will do the curl of f. So you'll take the partial derivatives and then cross product them, and you will get this equals x, negative y, and 0. And that's going to be our P, Q, and R for the formula we've been using. And so the only other thing we need to know is that Z can be written right here. Z is our g of xy, which is y squared minus x squared. Therefore, dg dx should be minus 2x, dg dy is equal to positive 2y, and the double integral becomes minus p, which is minus x, times dg dx, which is minus 2x, minus q, which is minus y, times dg dy, which is 2y, plus r, which is 0. All of that's on dA. Okay, so this is going to become, double negatives cancel, you get 2x squared. Double negatives cancel, you get 2y squared, dA. And what we're going to want to do is, we see this cylinder again, so we're immediately going to say r squared is 1, therefore r is 1. So we're going to have, we can factor out a 2 here. We're going to get 2 double integral of x squared plus y squared dA. But x squared plus y squared is r squared. We're going to put this in polar coordinates. So we're going to get 2, 0 to 2 pi. Radius goes from 0 to 1 based on this here. And this is just r squared, but then we have times r dr d theta to change it to polar coordinates. And this is an incredibly simple double integral to tackle. You should get out of this just pi. So that's using Stokes' theorem to calculate the curl of f dotted with dr. Now we have to get the picture. So to get this picture, we're going to consider the hyperbolic paraboloid z equals y squared minus x squared, and the cylinder x squared plus y squared equals 1. So just based on those two things, you can eliminate two of these pictures right away. And that is the cylinder. So this cylinder does not have a radius of 1. If you look at it, its radius is only 0.5. So that one and that one's gone, which leaves just this one and this one. Now how do we know which one it is from there? So if z is equal to y squared minus, let me make sure I'm writing this down right, y squared minus x squared, that's going to have a parabola that points down in the x direction. So it's a minus x squared, so this is going to point down, and in the y direction it is going to point upwards because this is positive. And that is not true on this one. So this one is flipped the other way. It's pointing up in the x and down in the y. So just by process of elimination, I don't recommend trying to graph this thing. Look at it and use process of elimination to hone in on this one right here. Okay, that would be part B. There's 3 parts to this. Okay, and then it says find parametric equations for this. So this is, there's not much to even write here. So we're going to use r cosine t, y equals r sine t. Now we recall from before the radius of the cylinder is 1, so this is just going to be cosine t and sine t. Now z was told to us as, and let me not write it wrong, I just started to, y squared minus x squared. Well, based on these x and y's, that means it's sine squared t minus cosine squared t. So here's your cosine for x, here's your sine for y, and then sine squared minus cosine squared for z. And you have to actually write the z equals and the y equals and the x equals. Okay, that's problem 4. Okay, for problem 5, we have a particle moves along line segments from the origin to 3 different points and back to the origin under the influence of the force field, and gives us the force field. Find the work done. Well, the work done is just going to be finding the double integral of our f dot dr, like we've done on all these other problems. And so we're going to have, we're going to have to find the curl and do everything else, but I want to draw this picture just to give us a better sense of what's going on here. So let's kind of try to draw this. X, Y, and Z. And the biggest numbers we need are just to 3. 1, 2, 3. Okay. So the first point it travels to so it starts at the origin and it goes to 2 in the x, 0 in the y. So it goes, well, let me put the points down, then I'll draw the curve. So then the next point's at 2, 3, and 1. So it's along this path. This is 3, and then 1 up would be about right there. Then it goes to 0, 3, 1, so it's 0 in the x, 3 in the y, and 1, so it's still the same height, but now it goes over here, and then it goes back to the origin. So if we were to draw this, it goes from here to here, this direction, goes from here to up here in this direction, and it goes straight across to there, and then it goes back down to the origin. So this is the movement, this is the path of the particle under this field. So it says the field is z squared 3xy and 5y squared. And I'm not even going to go through it. The curl of f you should be able to get fairly simply would be, this is 5. The curl of this f is 10y, 2z, and 3y. And that's P, and that's Q, and that's R. Make sure I didn't make any errors. That looks correct. So we're going to plug these into our double integral. The formula is minus P, which would be minus 10y. Oop, we're missing a step. So we have to find z, which is going to be, we're going to call g of xy, so we can solve for dg dx and dg dy. I should say partial g with respect to x. Okay, and from this picture, basically what you end up doing is you say, what's happening on the zy plane? Actually, that's for the limits. Let me see here. How did I argue this out? So z, if you look at what z is equal to, yes, so if you look at the zy plane, so imagine x is 0. Let me actually draw this over here. This is y, this is z. That blue dot over there is 1 unit in the z and 3 in the y. So the equation for this line is very simple. It is the equation z is equal to 1/3 y. So it's basically a slope of 1 over 3 in the y direction. So that is going to be our g of x, y, is 1/3 y. Which means dg dx is going to be 0. Then it's minus q, which is 2z, times dg dy, which is 1/3. Then it's plus r, which is 3y. And that's all dA. So that is the double integral. And so now we're going to, it's a pretty simple one, and we're going to replace z with what it is. So this first term goes away. This is going to be minus 2/3 times z, but z is really 1/3 y plus 3y, and I believe I did dy dx. Now you also have to reason out what your limits on x and y are. From this plane, you can see that y only varies from 0 to 3, and x only varies from 0 to 2. Okay, and then again, this is a pretty simple double integral. You've only got one variable, it's all linear, so you can take the antiderivatives and you should just get a number out of this, and it should be, for my problem, I got 25 even. So that's how you set up and complete problem 5. That one's not too bad. Okay, problem 6 looks kind of nasty, but it's not too bad. The field we're working with is, and this one they kind of buried the field in the line integral. So if we just break that out, you'll see how I got this. The field is just the first term here, y plus 4 sine x. The second term is the second term of the field, z squared plus 3 cosine y, and the last term is just x cubed. And once again, I'm going to say perform the curl, which is the cross product of partial derivatives with those three terms, and you should get negative 2z, let me make sure I'm looking at the right problem here, problem 6, negative 2z, negative 3x squared, and negative 1. So that's P, that's Q, that's R. Okay, now we have to come up with the G equation. Well, it tells us right here, Z, which is going to be G of xy, is 2xy. So we perform our double integral. We have minus P, so it's minus 2z times dg dx. Partial g with respect to x would be 2y, minus q, but q is minus 3x squared, times dg dy, which would be 2x, plus r, which is negative 1. And all that's on dA. So if we look at this, we're going to get double negative here, 2 and 2 is 4, times y times z, but with z we've got to replace that with 2xy. So it's times another 2 and times an x and a y. Then we got another double negative here, so it's plus 3 times 2 is 6, x squared times x is x3, and then we have minus 1. So just doing this combination here, we get 8x squared y. No, I did that wrong. It's xy squared, 2 y's, and it's plus 6x cubed, and it's minus 1, and it's dA. Should have had it d all along here. Okay, now because we're working with sines and cosines, and t goes from 0 to 2 pi, we're going to want to change this to polar coordinates. So we're going to get, and I want to make sure I'm not missing something here. Okay, so we're going to have, now I did miss something here. This curve, r of t, if you look at how this curve is mapped out, it actually goes down. So there should have been a negative, and so again, orientation matters here. So there should have been a negative carried along this double integral because of the nature of the curve, how the curve goes. Okay, so we just add that negative back in, and then we get negative double integral of, this is going to be 8, and we have we're changing x to r cosine theta and y to r sine theta, and in this problem we don't know what r is, so we just leave it unknown. So we get r cosine theta times r squared sine squared theta for y squared plus 6r cubed cosine cubed theta minus 1, and then we have times r dr d theta, and this is going to go from 0 to 2 pi, and the r we do know is bound from 0 to radius of 1. Okay, and how much of this do I want to show? If you plug in, if you do this antiderivative double integral, this one will be a bit challenging for you. I encourage you to try it. You should get this whole thing will reduce to simply pi. So the answer is really nice, but getting there is going to take a little bit of work because you've got cosine cubes and sine squareds and cosines and r's all over the place. But at this point, I think you would be able to do it. Okay, for problem 7, we are given a field to be, the field is x squared y cubed z and sine of x, y, z and the third term is just x, y, z. But for this one, we don't want to go down the path of the previous steps. What we want to do is do the one, I think we saw one of these, where we go from 0 to 2 pi of the field using a parametric equation, and in this case we want t dotted with the radius, the derivative of r of t dt. So this is the one we want to use. And we are going to notice in this problem that, let's see here, so it says part of the cone, y squared equals x squared plus z squared, lies between y equals 0 and y equals 3. So what we're going to get from that is that this is a circle of radius 3, so y is 3, and this is a circle in the xz plane. So it's a plane we're not used to drawing a circle in, but it is still a circle of maximum radius of 3. So we're going to come up with our r as radius 3 times cosine of t, and actually we're going to use sine for this one. And then the y component is just 3. And then the z component is going to be 3 cosine t. So because the circle lies in the xz plane, we assign 3 cosine t to z and 3 sine t to x. And then the derivative isn't too bad. We would have 3 cosine t, 0, and minus 3 sine t. The harder part is replacing f with this r of t. So it's got x squared is now going to be 9 sine squared t. But then it's times y cubed. Y cubed is going to be 27. But then it's times z, and z is 3 cosine t. So you can see how this can get a little messy, and we're replacing these x, y's, and z's with this parametric representation of this vector r. Now the middle term is sine x, y, z, so it's sine of x, which is 3 sine t, times y, which is 3, times z, which is 3 cosine t. That's all inside of a sine function. Then the third term is x, y, z, so it's exactly what this one looks like. 3 without the sine, 3 sine t times 3 cosine t. Okay, then, oops, I forgot to prime it. That's a derivative. We're going to dot this, dot product that with r prime of t. So we're going to get 3 cosine t times this first term, so this one times this one. This 0 is going to kill off all of that, so we don't have to worry about that. Then we're going to have minus 3 sine t times this one. And we're going to add them all up. So we're going to get, this is going to be 2,187, 9 times 27 times 3, sine squared t cosine squared t okay, so we get the 9 times 27 times 3 is a 2187. We have the sine squared and then cos t. Cos t is cosine squared t. Middle term goes away. I'll write it as plus 0. Then it's plus, minus. It's a minus 3 times, we get minus 3 times 3 times 3 times 3, which is 3 to the 4th, which is going to be just 81. And we have sine times sine, which is sine squared. And we have 1 cosine t. And so we're going to put that into the integral of 0 to 2 pi of this dt. And if you do that single integral actually, you will get 2187 pi all over 4. And I know I'm skipping some of these actual integrals, but this is the end of Calculus 3, and it's more about setup and trusting you know how to do an integral at this point. Okay, that will complete Chapter 6, Section 8.